the sheer number of joint replacements that are put inside the body is such that we get a very large number of retrievals, a very large number of those joints that actually fail. And what we'd like to do is to reduce those number of joint failures through the uses of new technology and, importantly, new testing regimes. We know from the recent debacle around metal on metal prostheses that the tests that we currently have weren't up to demonstrating the poor performance of metal on metal replacement. So in this project, we've focused on having adverse conditions for testing the joints more rigorously.
We've talked about ETH's contribution with the fluoroscopic data, and we have motion capture data, and these feed into a musculoskeletal model which provides joint loading. This then actually goes on to joint scale wear simulations, which have been developed at Leeds and Imperial College in London. They have the ability to predict how much material will be worn away over a certain number of cycles, but they rely on accurate input of motion and force data. And this is what we are now putting together. We're taking our results from ETH, the results from Leeds, insights into the modeling from Anybody, and the wear simulations from Leeds and Imperial, and making together a multi-scale, multi-physics simulation to predict wear.
I don't think computational wear simulation will replace physical wear simulations. What it allows us to do is to do more. For instance, this machine here, to do a 5 million cycle run, takes 3 months. We can do a 5 million cycle run computationally in parallel, and it'll take a matter of minutes or at most hours. So we've got the technology, therefore, to look at different points in parameter space and to try and identify those points which can cause an adverse reaction or an adverse scenario. Once we've got that data, we can then use it in our physical simulations to check whether that prediction is right or not.